Welcome to the Picture Language Seminar. We're very pleased today to have Ramon van Handel talking to us from Princeton. Ramon's former life involved being a student in experimental physics, and somehow he got to be a leader in random matrix theory, and is going to tell us today about non-asymptotic random matrix theory. Ramon, we're very pleased to have you, and you said you'd be happy if people interrupted with questions. So why don't you share your screen and start your talk?
All right. Well, thank you very much for the invitation. It's been a long time since I've done any physics, so I hope nobody asked me any physics questions. But I'm going to talk about random matrices, but I will say in advance that the kind of random matrix theory I'm going to talk about, there's fairly little resemblance to classical random matrix theory. And maybe the first thing I should do is to try to explain the context and what kind of questions we ask here. I don't come from random matrix theory. My interest is more coming from high dimensional phenomena and probability and analysis and geometry. And so we tend to ask somehow different questions than you would see coming, for example, from mathematical physics. So what is the goal of random matrix theory? Well, in principle, right, what is a random matrix? It's just a matrix filled with random variables, right? And we want to understand their eigenvalues, right? Understand eigenvalues, or the spectrum, let's say, of random matrices, right? So, but in order to be able to do that, we have to specify what kind of random model we have for random matrices, right? So in classical random matrix theory, if I'm going to caricature it a little bit, but basically classical random matrix theory is considered with a very narrow class of models of random matrices. Typically, these random matrices contain independent and identically distributed entries, or nearly independent and identically distributed entries, or another big class of random matrices are those that are invariant under symmetry groups, for example, under orthogonal transformations or under unitary transformations. Yeah, the distribution is invariant. And so these models are very special models, right? They give us a sequence of random matrices of increasing dimension, and one can study the behavior of the spectrum as the dimension goes to infinity, right? So these are, let's say, special models. But in return for having these very special models, we get we get essentially exact asymptotics, right? So the most classical example of this, right, is, for example, if I take a D by D, right, self-adjoint, for instance, right, random matrix with IID entries, and the natural normalization is that the mean is 0, and the variance is 1 over D. This 1 over D is just chosen so that the spectrum is bounded as I let D go to infinity. So, these matrices form a natural family of matrices of increasing dimension, and we can try to look at what their eigenvalues look like as I let the dimension go to infinity. And these are called Wigner matrices. Right? The behavior, this is the most classical model of random matrix theory, and their behavior is very well understood. The most basic result is that if you draw a histogram of the eigenvalues, right? So if I draw a histogram of the eigenvalues and I let D go to infinity, it'll converge to this beautiful distribution called the Wigner semicircle distribution. It goes from -2 to 2, and its density is exactly a semicircle, like this. Well, it looks very bad, but it's supposed to be a semicircle. So, asymptotically, the eigenvalues form this beautiful semicircle distribution. Now, if you look at this distribution is supported from -2 to 2, right? So it seems like the largest eigenvalue should converge to 2 and the smallest eigenvalue should converge to -2, but that's not stated by this result, right? Because this is a histogram. It says, right, what this result means is that if I look in some interval AB, then the fraction of eigenvalues in AB will converge to the area under the semicircle within that interval, right? It doesn't say anything about an individual eigenvalue, which is mass 1 over D, right? If you have D eigenvalues. But nonetheless, this was proved in the 50s by Wigner. in the 80s, it was shown that the largest eigenvalue of such matrices indeed converges to 2, and the smallest eigenvalue indeed converges to -2. These are harder results, right? But they are very basic in random matrix theory. But nowadays, this is just, this is just the tip of the iceberg. For these kinds of random matrices, random matrix theory has an amazingly detailed understanding of what is going on here. For example, what you can do is you can zoom into the spectrum of these matrices so that the typical spacing is of order 1, and understand the exact limiting distribution of the point processes eigenvalues near the edge and the bulk, these form determinantal processes. And okay, so one goes off into random matrix theory and is able to prove extremely detailed, exact asymptotic statements about the spectra of such random matrices, right? But the price you pay for this is that, you have to have a very special model of random matrices, right? And you have to have a sequence of them as the dimension goes to infinity in order to be able to study them at such level of detail, right? So this is, you are restricted to asking very specific questions about very specific models of random matrices. So my talk is not about this. In many ways, I'm going to talk about the opposite extreme. And these type of questions really don't arise from random matrix theory, but they come from other areas of mathematics. Suppose that rather than saying I take a matrix of IID entries, or that's symmetric under unitary transformations or something like this, I want to study random matrices with, to put it bluntly, totally general structure. Right. So, right. So I give you a D by D matrix. Its entries are random, but they're not identically distributed. They can have different variants. They can have correlations between them. And I don't want to impose, of course, I could take such models that have special, a special sequence of models as the dimension goes to infinity, but rather I want to ask the question, if you give me a random matrix and you tell me what is its pattern of the entries, right? What are the pattern of the variances and covariances, for example, of the entries? What can you tell me about the spectrum? And I do not want to impose structural assumptions that I'm looking at a particular model, right? Of course, this is a little bit too general, but we're not going to be that far from that. And as a guiding example, I want to take the following one. Suppose that X is a D by D. Let's make it self-adjoint. Right? Random matrix. And the only thing I'm going to assume about its entries is that they're jointly Gaussian. So I'm going to assume the entries are jointly Gaussian, but nothing else. I'm not going to assume that they have the same variance. I'm going to allow them to have arbitrary covariances, basically, right? So this is a matrix which can have basically arbitrary dependencies between the entries, arbitrary pattern of intensities for different entries. And now I want to say, okay, you tell me what is the pattern of the covariance of this matrix and the mean, for example, and then, I will tell you what does the spectrum look like, right?
May I ask a question?
Yes, of course.
By jointly Gaussian, do you mean they're pairwise, or all of them are altogether Gaussian? What could you clarify?
I mean, all of them are together Gaussian, but with an arbitrary mean and covariance matrix, let's say, all of the entries. We can go beyond this, and if I have time at the end of the talk, I will talk about non-Gaussian matrices. But even if you restrict yourself to Gaussian matrices, just to have you get cleaner results in this situation, even if you restrict yourself to that setting, it should be emphasized that this model is extremely general. It makes no assumption about the pattern of the entries of the matrix, right? So for example, right, you can take your favorite painting by your favorite artist, right? Let's say it's a black, grayscale painting, right? Just take a matrix, 300 by 300, and color each pixel, give it a variance according to the intensity of your picture. Now I've defined a random matrix, right? If I take the entries to be Gaussian, even independent, right? But their variances are allowed to be arbitrary, then I can take any picture and use it as the pattern of my variances of the matrix. So you take, your favorite Van Gogh painting, turn it into a random matrix, and now tell me what the spectrum looks like, right? This kind of model doesn't fall at all within classical random matrix theory, right? There's two problems. First of all, the pattern is completely arbitrary, right? So these matrices can, for example, be very sparse. They don't have any symmetries whatsoever, right? I mean, as soon as you do something like this, all of the symmetry goes out the window. And secondly, this connects to the title of my talk. This is a statement about a given D by D matrix. If you take matrices with IID entries, for example, IID Gaussian entries, there's a natural way of taking a sequence of such matrices of increasing dimension and letting dimension go to infinity. And then you can try to study their asymptotics, right? But if I tell you that you can take the D by D matrix with any pattern of variances, right? There is no natural asymptotic question. There's no natural way of taking such a matrix and taking the dimension go to infinity, because I've just described one given D by D matrix, right? So it's not even meaningful in such situations, right, to talk about asymptotics. There are no asymptotic questions because I haven't defined a sequence of matrices as dimension goes to infinity, right? So you can't even ask the type of questions that are asked in classical random matrix theory. The only questions that make sense are those that apply to the given D by D matrix. And you can imagine that the main thing we could do with such a matrix is prove some sort of inequalities for how the matrix behaves, right? Because I can't take any limit as D goes to infinity because I don't have a sequence of models as D goes to infinity. I have whatever data you gave me, and you have to somehow describe the behavior of this matrix according to that data. Does that make sense? So it naturally leads you to ask different types of questions. So these kind of models are very general, but in fact, if you don't look in random matrix theory, but in other areas of mathematics, both pure and applied, these kind of matrices show up a lot. So originally, these matrices were studied in functional analysis and in operator theory, dating back to the 70s and 80s. And more recently, such matrices have been extremely influential in applied mathematics. They lead to a theory called the matrix concentration inequalities, which if anybody has studied machine learning or some topic like that, these are like bread and butter results that are being used as black boxes all the time to study applied mathematics. You know, typically the type of models that show up in theoretical computer science and the analysis of algorithms and statistics, they are not matrices filled with noise, with white noise, which is basically what classical random matrix theory is about. But these are matrices that have some sort of underlying structure that's part of the that comes from the problem that one is studying, right? And so one needs to have general tools that allow one to study matrices that are not highly, that are not pure noise, but have some underlying structure. And in many situations, one is stuck with a model that's basically as general as what I'm describing. Okay, so
But I think being Gaussian means that essentially, in terms of physical language, you're not assuming any kind of interactions. So there's no non-linearity. So I'd presume that there will not be some nonlinear effects. Is that true?
no, I mean, and a Gaussian has quadratic potential. Of course, there can be interactions, plenty of interactions, but the interactions are quadratic, right? So I can talk about the non-Gaussian case at the end if I have time, but the Gaussian case is extremely general already. Okay, so there can be plenty. The covariances can be arbitrary, right? I mean, but of course, Gaussians are a special case of more general phenomena, and one is interested also in many situations in non-Gaussian problems, and we can handle those as well. But one has to formulate carefully what's the what kind of models one is looking at and how one studies them. Okay, so it turns out to be a somewhat separate problem, and I don't want to focus on it right now because the main difficulties that we're going to face already arise over here in the Gaussian case, and it gives the cleanest kind of results. Okay, so I'm going to focus on that for now. So good. So let's look for the foreseeable future. Let's just look at this case of Gaussian random matrices, right? So I'm giving you a Gaussian random matrix. I'm even assuming it's self-adjoint just so it has real eigenvalues, but I'm not making any assumption about the pattern of variances and covariances of the entries, right? So you can have arbitrary variance pattern, arbitrary dependencies. Now, if I don't make any modeling assumptions, what could you possibly hope to say about such a model? It seems like such a matrix could behave in basically an arbitrary way, right? So, the common wisdom for such models is that we can, in fact, say things about them, but those things we can say about them are relatively weak. But nonetheless, they're useful in many applications. So the classical result in this setting is the so-called non-commutative Kinshasa inequality of Lust-Picard and PCA from the 1980s. And it states that we can understand at least the range of the spectrum, right? So for example, for Wigner matrices, right, that I had on the previous slide, the semicircle distribution of the largest and the smallest eigenvalue showed that the spectrum is between -2 and 2, right? So let's say that we have now an arbitrary random matrix, right? Maybe we can't predict exactly what the spectrum will look like, but at least we would like to know what range the eigenvalues lie in, right? So we could hope to narrow that down to have some inequality that says that the eigenvalues lie in a certain range. Right? Now, it turns out that even that is rather difficult, but one can pin it down up to some small factor. Whether it's small, you can decide for yourself. So here is the inequality. This norm that I write here is just the largest thing, the maximum of the absolute values of the eigenvalues. It's the operator norm of the matrix, right? So this describes the range of the eigenvalues. By the way, this theorem, as I'm going to write it, also assumes the mean is 0. Later, I'm not going to assume that. So how do we bound this? It turns out that this is upper bounded and lower bounded by basically the same quantity, which is the norm of the expectation of x squared, okay? So there's a fundamental difference between this and this, right? This is the largest absolute value of the eigenvalues. That's a very complicated nonlinear function of the entries of the matrix, right? But here I took the expectation inside the norm, right? The expectation of x squared, this is a very simple object. This just depends on the variance pattern of the matrix. And this is something that you compute explicitly in any example. If I give you the covariance of the entries of the matrix, right? Then you can compute this quantity on the right-hand side over here. It's a deterministic quantity. So you should not confuse these two quantities. On the left-hand side, the expectation is inside the norm, right? This is like the variance of the matrix. And on the right-hand side over here, I'm talking about the eigenvalues of the matrix, which are very nonlinearly dependent, right? So it would be great if we could bound from both sides by this quantity that we can explicitly compute, but we can more or less do that. So here it is again. But on this side, we have square root log of the dimension of the matrix. So up to a factor of square root log of the dimension of the matrix, we can at least estimate the range of the eigenvalues. Right? So on the one hand, this is a very depressing result, right? Because as the dimension of the matrix goes to infinity, the upper and the lower bounds diverge from each other, right? So we get less and less information about the behavior of the spectrum as the dimension gets larger and larger, right? That's exactly the opposite as in classical random matrix theory, right? But on the other hand, this is a very impressive result because this result makes zero assumptions on the structure of the matrix. It's only assuming the entries are jointly Gaussian. It doesn't make any assumption whatsoever about the variance pattern. There's no assumption whatsoever about the dependencies, right? So this is basically saying that even if we make absolutely no assumption on the model whatsoever, except that it's Gaussian, we can still pin down the range of the spectrum up to only a factor that's only logarithmic of the dimension, right? So for example, in computer science, people often completely ignore logarithmic factors. You know, everything is about polynomial time, right? So anything that's logarithmic is completely ignored, right? So in some applications, this is a very strong result because it allows you to assume nothing and get a very strong kind of bound on the type of object you're dealing with. But from the point of view of random matrix theory, this is a very embarrassing result because it basically says nothing as dimension goes to infinity. And in fact, these bounds aren't even correct for the simplest possible models of random matrix theory. So let's look at some examples. So if we go back to the example of the Wigner matrix, right? So now what is X, right? So we take a matrix, we fill it with IID Gaussians, right? So these are normal 0, 1. These are IID normal 0, 1. I have to normalize it by 1 over square root d. So we saw in the very beginning that the expected norm, right, the range of the spectrum is exactly 2 plus little o1, right? Because in the limit, as d goes to infinity, the eigenvalues are from -2 to 2, right? As in the semicircle distribution. But if you compute the expectation of x squared, this is very simple in this case because the entries are IID. This is exactly the identity matrix, right? So the norm of the expectation of x squared is 1, right? So in this example, if we were to go back to the previous slide, right, the lower bound over here is sharp up to a constant because in the middle we have 2. On the left-hand side, we have 1, right? But on the right-hand side, we have square root log d, right? So this non-commutative Khinchin inequality doesn't give us the correct upper bound on this range of the spectrum. Even for Wigner matrices, it's a factor square root log of dimension off from the correct behavior. And this is the world's simplest model of a random matrix, right? So we see that we already lose square root log d in the upper bound. The upper bound predicts that the norm should be at most square root log d, but actually the norm converges to 2. On the other hand, here is another model of random matrices. Suppose I were to take a diagonal matrix with IID standard Gaussians on the diagonal and 0 everywhere else, right? Then the expectation of x squared is still equal to the identity, right? But now, what is the expected largest eigenvalue of x? Well, that's just the expectation of the maximum of IID Gaussians, which is of order square root log d. And now we have the opposite behavior, right? Where the upper bound is sharp, right? Because the norm of a diagonal matrix with IID Gaussian entries on the diagonal is square root log d, but the expectation of x squared is the identity. So now we need to have the square root log d, right? The upper bound is now sharp, and now the lower bound is suboptimal. But the basic parameter, this variance of the matrix that we use as our basic parameter, is the same in both of these examples. So these examples show that this inequality cannot be improved as stated, right? If you allow a completely general structure, both of these very different examples are examples of random matrices that are jointly Gaussian, but with arbitrary variance pattern. But they behave very differently from the point of view of the range of the spectrum. So it shows that this imprecision in the type of questions we can ask about these matrices is somehow very intrinsic to this problem, right? You cannot hope that both of these matrices, a Wigner matrix and a diagonal matrix, behave in the same way from the point of view of their spectral theory. Right? So that's a very basic fact. And so we have this inequality. It is a very strong inequality in that it assumes nothing, and it's a very weak inequality in that it doesn't accurately capture almost anything, right? And it's been a long-standing problem in this area to find inequalities that improve on the non-commutative Pynchon inequality, and that are better able to predict the behavior of these matrices, right? For example, we would dream to have an inequality that can see the difference between the diagonal matrix and the Wigner matrix. In the case of the Wigner matrix, would at least predict that the range of the eigenvalues is bounded as d goes to infinity, without falling into this pitfall of the diagonal matrices, right? And people working in this area have looked for a long time for these type of inequalities, and basically nothing has appeared really, except we made a lot of progress a few years ago on studying the special case where the entries are independent. Then you have additional tools at your disposal, and one can make a lot of progress. But for a completely general model where you're allowed to have dependencies between the entries, basically nothing was known, really.
Okay. Sorry if I may interrupt. I have to leave in 3 minutes.
Okay.
Marius Junge here. So you have, of course, results for blocks of these things, right? These operator value. If you take blocks of matrices, if you know that they have a block structure, then there are more results, right?
Yes.
In the operator valued setting, right? If you do matrices.
I'm going to talk about that later.
Yeah,
so,
I have to leave in 5 minutes. I have a meeting. So that's why I brought it up now.
There are special models, which I'm going to talk about later, which are again asymptotic, that allows you to get asymptotic behavior, right? So if I take, for example, a D by D matrix with fixed D, but I replace every entry by itself by an N by N Wigner matrix, then I can let N go to infinity and predict the exact distribution in the limit, right? This allows you to have some sort of limited inhomogeneity in the matrices in an asymptotic sense.
Sorry to... I just have to leave in a second. You can also do it for fixed, not in the limit. You can also have some Pynchon type inequalities if you fix the size.
Right. Then there is going to be some trade-off. But these kind of block matrices basically never appear in the type of in the type of questions that I have seen. They are artificial in some sense, in the sense that they are introduced because we can prove things about them, right? But they're not particularly relevant, I think, to the type of questions that are showing up in other fields. So as you have to leave in 3 minutes, the main upshot of this talk is that it turns out that these behavior of these block matrices actually turns out to appear when the blocks of size 1. And that is the main upshot of this talk. Okay, but that is the main idea. But that requires us to go beyond what is okay. So that's the but you know, now I'm really running ahead of myself.
So
yes,
there is no phenomenon so analogous to the phase transition, like some
give
singular.
Give me some time and I will get probably there. Yes. Okay. Yes, there is such a phenomenon, but I cannot explain that yet because I haven't gotten anywhere yet. Okay. So
okay.
So we would like to right. In principle, we are unambitious. Okay. We have such general models that we cannot hope to have the type of results that people have in classical random matrix theory, right? So but we would like to have inequalities that at least capture the right order of magnitude of the spectrum in at least, you know, reasonable examples, right? I mean, that is the problem that we wanted to do. And what is sort of surprising, very surprising to us, is that once we understood the right approach to this problem, it turns out that we could do much, much better than that. And in fact, in many situations, we get sharp results that normally you would only expect to be able to get in an asymptotic regime. We are able to get it in this non-asymptotic setting for fixed matrices. And in order to do that, you really have to change the perspective in the way that one thinks about these type of non-asymptotic inequalities. And I want to start next by describing the high-level idea of how you do that. I don't have time in an hour talk to give you a full-blown technical description of free probability theory, which we're going to need. But I think that a better way to think about this is as a sort of, just in terms of some sort of high-level idea. So here is how it's going to work. So we start with a fixed given random matrix. Okay, so this random matrix X, right? It's a D by D, right? Random matrix, jointly Gaussian entries. And take it to be self-adjoint just so we have real eigenvalues. So this is not super important, all right? Now, what we're going to do is rather than prove inequalities for this matrix, like the spectrum lies between the expectation, the norm of the expectation of X squared and something else, right? What we're going to do is we are going to associate to this matrix an object called X free, which you should think about as the platonic ideal associated to this matrix. So what is this X free? So this is a random matrix, right? This X free is a certain deterministic infinite dimensional operator whose spectrum models that of X. Okay. So there is just a recipe. I start by giving, you give me any random matrix X D by D with jointly Gaussian entries. It doesn't have to have mean 0 now, right? You give that to me, so it's defined by its mean and its covariance matrix of its entries, right? And given that data, I construct for you a certain object X free, which is some sort of infinite dimensional operator, right? And the idea is that somehow the spectrum of this infinite dimensional operator should describe what is going on with this random matrix. Okay. Now, this infinite dimensional operator, we didn't invent that operator. It's a standard construction in the theory of free probability. What you do is you replace basically every entry of the original D by D matrix with a non-commutative object, which is called for those of you who know, you just replace the Gaussian entries of the original matrix by a semicircular family with the same mean and covariance. So what you do is you replace the original random variables that are entries of this D by D matrix, you turn it into a D by D matrix of some non-commutative objects, okay? And these non-commutative objects are very well known in free probability. And in fact, free probability does much more for us. The theory of free probability it provides a kind of calculus that allows us to compute the spectrum of X free basically by explicit formulas. the spectrum of X free explicitly. So there are exact formulas for the spectral distribution of X free, of this infinite dimensional operator, for the edges of the spectrum of X free. All of these things, there are exact formulas. Maybe I'll write one down later if I have time, that allow you to compute exactly what the spectrum of X free looks like. The spectrum of X, it's a random object, right? The spectrum of X we cannot compute exactly, but the spectrum of X free we can compute exactly. And what we hope is that the spectrum of X free behaves like the spectrum of X, right? So just to give you an example, right? So if X is a Wigner matrix, right? Then we know that the histogram, so the histogram of the eigenvalues converges as the dimension goes to infinity to the semicircle, right? This is the most basic result, let's say, in random matrix theory, right? So if I take a limit as the dimension goes to infinity, then the spectrum looks more and more and more like the semicircle, right? But the spectral distribution of X free, if I take the X free that associated to the Wigner matrix, actually is equal to the semicircle, right? So you should think about X free as being the ideal situation. It describes the spectrum of X free, actually described what the limit looks like, right? The spectrum of X free, the distribution of the spectrum of X free is equal to the semicircle. There's no limit, right? So you can think about such a result as saying that a sequence of Wigner matrices whose dimension goes to infinity, in the limit, the spectrum is described by the spectrum of X free. So what does this have to do with what's on the previous slide? Here we don't have a sequence of matrices whose dimension goes to infinity. Here we have one given D by D matrix, right? And I define this X free. So what does the theory of free probability tell us? Well, the classical result in the theory of free probability is what Marius was referring to earlier, is that free probability theory, people have learned how to take this random matrix and produce from it a sequence of new random matrices of increasing dimension whose spectrum converges to X free, right? What you do is you take this D by D matrix. Every entry is Gaussian, a scalar Gaussian. But what you can do is you can form a new random matrix where I replace every entry of this D by D matrix by an N by N Wigner matrix with the same mean and covariance as the original matrix. So now you get a matrix of dimension D times N, right? Because you replaced every scalar entry of the original matrix by a block, right? By a Wigner block. And if you take the size of the blocks going to infinity, then it is known that the spectrum of those new random matrices will converge to the spectrum of this X free, which is a known object in free probability theory. Right? This is the theory of block matrices, right? But when you create these blocks, that doesn't say anything about the original random matrix, right? We don't care about these block matrices. We want to understand a given D by D random matrix with scalar Gaussian entries, right? So the theory of free probability directly does not tell you anything about that. It only tells you what happens if you somehow blow up the original matrix and make it non-commutative. Now, the key phenomenon that we discovered is that actually this, you don't need to blow up these blocks. Under very weak assumptions, the spectrum of X already behaves like the spectrum of X free, not blowing up the blocks, right? But I just give you a D by D matrix, and we have conditions, quantitative non-asymptotic conditions, under which the matrix X itself already behaves like its Platonic ideal. And as soon as this is the case, that means that you can use this ideal, this Platonic ideal, to compute with very high accuracy the behavior of the given random matrix X in dimension D in a non-asymptotic sense. Okay, so this is the basic upshot of the theory. And in fact, this is not one theorem that describes what I'm telling here. We have a whole sequence of theorems that are based on the same techniques and the same methods of proof that show that in various different ways, the spectrum of X behaves like the spectrum of X free. Okay. So let me just write down one very simple, one special case of one theorem of this kind, which is an example of what our theory can produce. So this is with Afonso Bandeira, Boedihardjo, and myself. I'm writing down this theorem because it can be directly compared with the non-commutative Khinchin inequality that I wrote before, and therefore we can see how it improves in the non-commutative Khinchin inequality. But later on, I will explain that we can prove much more precise things than what I'm about to show. So in order to explain what is going on here, right? So here is the inequality. So in order to compare this with non-commutative Khinchin inequality, I'm going to try to bound the same object, which is the norm of X, right? The range of the spectrum, the largest absolute value of the eigenvalues of the matrix X. So the inequality that we get from our theory is the following. So this is bounded by. Now on this side, we get with this inequality is not at the universal constant. This is with constant 1. This is a sharp inequality. It's bounded by the largest absolute value of the eigenvalues of X3, or of the spectrum of X3, right? So this is the Platonic ideal, what the Platonic ideal would suggest. For example, if X was a Wigner matrix, the spectrum of X3 would be the semicircle, so this would be exactly 2, right? And then we have a remainder term. And in this remainder term, there is some universal constant. And then we have some parameters. So here's the previous parameter that we know and love. And here's another parameter that I have to explain to you in a moment. And we have something now, some power of log D. Here it is. So you see, we know that there should be a power of log D somewhere in this inequality. Because if we were to plug in a diagonal matrix, right, then X3 would not describe the behavior of X. We already saw that in an example, right? So we know that somewhere there has to be a log D in this inequality. But in this inequality, there is a new parameter, which is the norm of the covariance matrix of X. And what is the covariance matrix of X? So X is a D by D random matrix, so it has D squared entries, right? So we can just think of those D squared entries as being a bunch of Gaussians, and they have a covariance matrix. So this is the D squared by D squared covariance matrix of the entries of X. So if we just think of the matrix of the entries of the matrix X, the D squared entries as a Gaussian vector, it has a D squared by D squared covariance matrix. And we can take its largest eigenvalue. That's the norm of the covariance matrix of X. And this new parameter is often much, much smaller than the size of the largest eigenvalue of X itself. And whenever that is true, this second term here will become negligible, and it will show that the behavior of X itself is exactly like that of its Platonic ideal. So it's a little bit hard to see, right? So let me just observe that there is a basic inequality from free probability. We could do much better than this. We have exact formulas, but a very simple inequality that you can prove using free probability is that the norm of X3 is bounded by 2 times the quantity that appears in the non-commutative Khinchin inequality. Right? So this shows that the expected norm of X is of the same order as the expectation, as the quantity in the non-commutative Khinchin inequality without the log D, right? So in the non-commutative Khinchin inequality, we can remove the log D, provided that the second term is much smaller over here, so that the norm of the covariance matrix of X divided by the norm of the expectation of X squared is much, much smaller than 1 over log D cubed. But this condition here is a very, very weak condition. So for example, for Wigner matrices, I don't know why my pen is not writing. So this is a D. It's not writing because seems my pen either ran out of battery or there's something horribly wrong with it. No, it says 100%. So, there we go. So just for reference, for Wigner matrices, the quantity over here is 1 over D. So this quantity over here, right, we can be very, very, very far from Wigner matrices. and still have our random matrix X behave exactly like its Platonic ideal. Right? And I will give some examples in a moment. But this shows that there is this other parameter, which is the norm of the covariance matrix of X, which controls how close the random matrix X is to behaving like its Platonic ideal. And as soon as you have this very weak condition over here, then basically the classical random matrix type behavior enters the picture. And that allows us to systematically sharpen all of these classical inequalities without, you know, doing something impossible, right? Because what happens, for example, for the diagonal matrix example, which clearly doesn't behave like a random matrix, is that the diagonal matrix is exactly a case where this quantity over here on the left-hand side is too large, and it exactly eliminates those examples that are counterexamples to having good behavior. So this is a basic idea. So I just want to give you some, I mean, you would have to digest what these inequalities are saying in order to really understand how to use them. But mainly, I want to give you a couple of examples to emphasize that these kind of inequalities are very easy to use, right? So we can introduce very simple models of random matrices where these kind of inequalities allow us to prove things that there was no way to prove before having such a theory, right? Even though this object X3 looks a little bit abstract, right? So let me give you a couple of very basic examples of the kind that you will see in applied mathematics, for example. You know, applied mathematicians use these kind of examples a lot, right? So suppose that you have a random matrix, D by D, and let me call its columns. Let me call its columns X1, X2, right? So its columns X3, etc., until XD, right? So suppose you take such a random matrix that has independent columns. Right? So the ith column is a random vector, right? So let's say it's Gaussian with mean 0 and covariance Ci. So Ci is the covariance matrix of the ith column, right? And I took them to be independent. Of course, this matrix is not self-adjoint, right? But it's very easy to turn this into a self-adjoint matrix using some trick that I'm going to ignore, okay? But this is not a big deal. So I've here assumed nothing except for Gaussian, and I've assumed now in addition that the columns are independent, right? But that still allows me to have any kind of dependency inside the column. Now, if you just plug this model into our inequality and use some crude bounds on the free probability quantity that we get out, you get that the expected norm of X is bounded by what? Well, it's something very explicit. So you have two terms. It's the sum, it's the norm of the sum of the covariance matrices plus the maximum of the trace of the covariance matrices. And then you get a third term. There is some constant times the max of the norm of the covariance matrices times some logarithmic factor. So you see the lower, or this last factor, this logarithmic factor, right? This is what controls how good this matrix, you know, how much this matrix behaves like its Platonic ideal. But you see that the parameter that naturally arises here, which is the maximum Euclidean norm, sorry, the maximum operator norm of the covariance matrices of the column, it is typically much, much smaller than the leading order behavior, which is the behavior of X3. Right? Because, for example, already here you see that one of the terms in the behavior of X3 is a maximum of the traces of the covariance matrix. So, of course, if each covariance matrix is rank 1, if the covariance matrix of the columns is rank 1, then the trace of Ci will be of the same order as the norm of, will be the same as the norm of Ci, right? So that happens if you take a diagonal matrix. So if I take a diagonal Gaussian matrix, then X1 will just have a Gaussian in the first coordinate and the 0 everywhere else. The second column will have a Gaussian in the second coordinate and the 0 everywhere else, etc. Right? Then the covariance matrices of the columns are each rank 1. But in that case, we know that we cannot have good random matrix behavior. But as soon as the, let's say the covariance matrices of the columns have rank, which is just by log of the dimension larger than what is just something like log of the dimension, that's already enough to have this leading order behavior dominate and have the second order term be negligible. And in this particular case, there is also this term over here, which can also be much, much larger than the maximum of the norms, right? Because this behaves like the sum and this behaves like the maximum. So you see, of course, we have to eliminate diagonal matrices. In the case of diagonal matrices, this term over here dominates. But it takes very little for that term over here to be negligible compared to the leading order behavior. And in that case, this inequality actually turns out to be sharp. You can find the lower bound, which is of the same order as the leading term. Okay, so that's, it's a very basic example, but it shows that we can somehow effortlessly prove inequalities that are, you know, in settings that we really didn't have any tools to study before introducing this kind of machine. I have, do I have 10 more minutes or so? Is that right? Is that okay? Yes?
That's okay.
All right. So let me give you another example. This example is very classical, but I just give it to show that we can reproduce certain things that would be hopeless to reproduce without a sharp theory. So here I'm not saying something new, but of course, the theory that we have would allow us to prove much more general forms of this example. So this is a classical example due to Baik, Benarous, and Péché. People who have studied random matrices know very well what I'm about to say. Suppose that we take a random matrix X, which is what? It's a Wigner matrix. So here I take a regular Wigner matrix. Classical, right? IID Gaussian entries up to symmetry. But I add to it a non-trivial mean. I add to it a rank 1 matrix, right? So theta is some parameter more equal than 0, and V is in the unit sphere. Okay, so I add to it, this is a Wigner matrix to which I added a rank 1 perturbation, right? So I added basically one eigenvalue, right, to this random matrix, a deterministic eigenvalue to this random matrix. So what happens here with this eigenvalue? So this behavior is very well known. If you let D go to infinity, here it makes sense because I have a sequence of models that depend on D, right? So what happens is that when theta is small, this new eigenvalue caused by this rank 1 perturbation, it is hidden inside the bulk of the spectrum of the random matrix and you do not see it. But when theta is sufficiently large, this eigenvalue pops out of the bulk of the spectrum and you have a phase transition. So it turns out that, right, if I draw the histogram of the eigenvalues of this matrix, when theta is less than 1, all you see is the semicircle. And this rank 1 perturbation is hidden somewhere inside of here. But as soon as theta is more than 1, you still see the semicircle, and there is a single outlier eigenvalue at location 1 over theta plus theta that pops out of the bulk. And you see a single outlier coming out of this, out of the bulk. So this is something that you could never see if you only had equations up to universal constants, like the non-commutative Khinchin inequality, right? You would never see a sharp transition behavior. But this behavior is perfectly reproduced by X free. So it turns out that if you compute the limit as D goes to infinity of lambda max of X free, it's exactly 2 if theta is less or equal 1, and it's 1 over theta plus theta if theta is more than 1. And why can we do this computation? This is the X free associated to this model X. Why can we do the computation? Well, it's because we actually have an explicit formula, an exact formula for lambda max of X free due to Lehner, which says that lambda max of X free, well, there's some sort of variational formula for it. It's the infimum over positive definite matrices of the lambda max of the expectation of M inverse plus the expectation of X plus the expectation of X bar M X bar. Oops. So M X bar, where X bar is just X minus its mean. Okay, it's some formula, but it shows that the largest eigenvalue of the free object of the Platonic ideal has an exact expression as a variational principle. And once you have this variational principle in hand, it's very easy to do computations like this. You know, it's a few lines. You can do computations like that. And because this is a Wigner matrix, right, the norm of the covariance matrix of X divided by the expectation of X minus the expectation of X squared is of order 1 over D. So we're very far into the regime where the free behavior sets in. And we effortlessly reproduce the appearance of this phase transition of Beitman-Arousse and Péchet. We cannot reproduce the behavior that they have much more detailed information about, for example, the fluctuations of the largest eigenvalue. They can get that because this is a Wigner matrix. But in principle, we could replace this Wigner matrix by something much, much weaker. For example, an extremely sparse matrix. The entire theory of Beitman-Arousse and Péchet would go out the window. But this type of theory would keep going through and would produce the same kind of behavior. Right? So it is just showing that even classical things like this, which we could never hope to have if we had a non-exact theory, right? One that is not sharp, we can start reproducing it once we have the right approach to thinking about these kind of problems. So, you know, I have focused on stating these results in a way that is easily comparable with the non-commutative kinship inequality. But I just want to end with kind of summarizing, at least very vaguely, what kind of things we can prove using this machine. Okay, so here is some sort of overview of what we can show. Okay. So we have this single condition, which says that the norm of the covariance matrix of X divided by the expectation of X squared, right? This is the basic parameter, is much less than 1 over log D cubed, right? So this is the basic condition under which the theory sets in. When this is not true, maybe with some other power, I mean, one would maybe expect to have the log D rather than log D cubed. But as soon as this quantity is too large, we do not actually expect that the random matrices will behave like their Platonic ideals, and we have many examples to show that, right? So this something like this condition is very natural. And for Wigner matrices, again, the left-hand side here is 1 over D, right? So one can have very sparse matrices, for example, that still satisfy this, and they're very far from Wigner matrices. As soon as we have such a condition, what happens? Well, then we can show that X behaves like X free in many different ways. First of all, the spectral distribution of X is approximately the spectral distribution of X free, right? So not just can we say something about the norm of the matrix, we can actually talk about the entire histogram of the matrix. So the histogram of the eigenvalues of X will behave almost exactly like the histogram of the eigenvalues of X free. Now, in general, the histogram of the eigenvalues of X free is no longer a semicircle if you have a non-homogeneous random matrix. But free probability, again, allows you to compute it explicitly in terms of the solution of certain quadratic matrix equations. So typically, the spectral distribution of X free might look something like this. Well, it cannot look like that. No, it can look like that, right? It's some sort of bunch of weird blobs. So the spectral distribution of X free might look something like this. It's a bunch of weird semicircular blobs, but they can have things sticking out of them, right? And this is the spectral distribution of X free. It can be computed using some sort of explicit equation, right? And our theory says that as soon as this condition is true, the histogram of the eigenvalues of X will look very close to this. Right? Secondly, as soon as this is true, there are no eigenvalues in the gaps. Right? So for example, the result about the norm says that if this is the edge of the spectrum, right? This is the edge of the spectrum of X free, then the result about the norm says that there cannot be any eigenvalues of X out here, right? Because the norm of X, the largest eigenvalue of X, has to be very close to the largest eigenvalue of X free, right? But our theory also shows that there could be no eigenvalues in these gaps between the different bulbs in the spectrum. Right? So this not just does the histogram of X look much like X free, but the support of the spectrum also looks very close to the support of the spectrum of X free, which means that there can be no outlier eigenvalues beyond what is predicted by the free probability ideal. Right? Third, we have the same conclusions for polynomials of such random matrices. So suppose I take a bunch of random matrices, x1, x2, x3, x4, etc., that are independent, and all of them satisfy this condition here on the left. then I could take any non-commutative polynomial of these and look at the spectrum of this non-commutative polynomial, and we have very similar conclusions for those. So in particular, if you think, for example, about sample covariance matrices, which appear in statistics, these are quadratic polynomials. And the theory goes through exactly for these kind of things. And you could take really any non-commutative polynomial and have the same kind of conclusions happening for these things. And this, in fact, is it turns out in free probability to lie very deep. There was a very seminal paper by Hagerup and Thorbjornsen many years ago, around 2005, I think, where such a statement about polynomials was proved for just complex Wigner matrices. And that result made, it was very important in free probability. It disproved certain conjectures in operator algebras. But now with this theory, it turns out that this kind of behavior is not something very special about very specific models of random matrices. Almost any random matrix satisfies such conditions, which is something that was really out of reach of the theory so far. And fourth, this is non-asymptotic, right? So all of these statements, which I'm making here, all of these statements are witnessed by explicit inequalities that capture quantitatively for a fixed D by D matrix how close each of these statistics are to their ideals, right? So this is really something, if you're, for example, working in applied mathematics, that you can stick into an analysis of an algorithm or of a statistical procedure and use it in order to prove other results. Right? So this is a basic overview. I have also focused on Gaussian matrices. There are also non-Gaussian versions of this, but I do not have enough time to talk about them right now. But the theory is not restricted to Gaussian random matrices, and it turns out one can get non-Gaussian type of theorems, which are in fact very close to the kind of models that are already being studied in matrix concentration inequality theory for non-Gaussian random matrices that are well known in that setting. And here we can get the same results also in that case. So one is not restricted to the Gaussian cases, but that is really a separate story that I would have to tell separately. So on that note, let me end there, and I'm very happy to take questions.
Well, thank you very much, Ramon. You made a very beautiful introduction to a new set of problems which are interesting, and to solutions of some of these problems. So I'd like to open the discussion and ask that people who talk show their face. So Victor, you have a question.
Yeah, I have a question. The most important actually question: how do you construct X3?
Yes, exactly.
So I have avoided answering this question. Can you see my screen again? Oh, there it is. I've avoided answering this question because the way we construct X3 requires some objects from free probability theory, and let me just write how we do it. How we do it is very simple.
Okay.
If you know what the words mean that I'm going to use, right? So if X D by D matrix, right? So its entries are what? X11, X12, right? X13, etc. Right? They're jointly Gaussian. Right? So their mean is 0, or no, their mean is whatever it is. Mean is given, and the covariance between two entries is given, right? These are the problem data as described by the mean and the covariance, right? So what we do is we let, for example, how shall I call them? Let eta ij, right, be a semicircular system, with the same mean and covariance as xij. So the semicircular system, these are certain operators. They can be defined either on a C-star algebra or in a Fock space, in a free Fock space. So they appear, for example, from quantum field theory, or they can be viewed as elements that live in a C-star algebra. And they are some sort of infinite dimensional operators. And the key point is they don't commute with each other. They're non-commutative objects. And we just define X free This is just the matrix where we take the same, right? So this is a D by D matrix. So this is a D by D matrix, but the entries are now not random variables, they're not Gaussians, but they are these non-commutative objects. Right? So this is how we construct them. And it's a very explicit construction if you know what a semicircular system is, and otherwise it's something one can look up. But let me emphasize, so you know, this is a construction from free probability that is known, but the kind of equations that one uses to compute the spectrum of these objects are also very well known in mathematical physics. Because, oh, where did I go? So for example, the spectrum of X free can be computed using so-called matrix Dyson equation. Which, if you look at the mathematical physics literature, you will find lots of papers using the same kind of equations to describe random matrices. So these objects from free probability their spectrum is exactly given, right? So if one looks at their Green's function, their matrix Green's function, it satisfies a set of quadratic equations, which is explicit and one can simply write down, and the existence and uniqueness theory of these things is well understood.
But can you say something about at the IJ? You know, we're not afraid of Fock spaces, so perhaps you can say something about it.
So, yes, I mean, they are defined in terms of the, you take a free Fock. So if the covariance is the identity and the mean is 0, then this would be a free semicircular system, okay? And you can simply generate those by taking a free Fock space and taking these to be the, you know, AI plus AI adjoint, where AI are the annihilation operators on the free Fock space. That's a construction of these objects. I think maybe a better way to think about them is combinatorially, and that will give you more insight, and in fact will connect the most closely to the topic of this seminar, which is mathematical picture language, right? So if you recall, so if I have, for example, forget about the random matrix, let's X be a Gaussian vector with mean 0 and variance sigma, right? And suppose I wanted to compute some mixed moments of the entries of X, right? Then there's a so-called Wick formula, right, which says that I can compute this by taking the sum over all pairings of K, right? And then I would take the covariance, maybe sigma is a bond because it looks like a sum. Oops. All right, this is a new iPad and I'm still getting used to what I click on. Let me call it C, right? Pairings of K, right? And then I get the product over all pairs of C, IA, IB, right? So to draw this in a nice picture, right? I take K points, right? And I can draw, do I have an even number? Yeah, so I can draw, for example, a pairing. It might look like this, right? So that's a pairing. And associated to this pairing, I just take the product of the covariance of these two guys and of these two guys and of these two guys. And if I sum over all possible pairings, then I get exactly this mixed moment. This is the Wick formula for the moments of Gaussians with an arbitrary covariance matrix.
Okay.
So these semicircular objects are exactly the same, but instead of having the sum over all pairings, you only get the sum over non-crossing pairings. So here, this over here is called a crossing, right? So a non-crossing pairing would look like this. Right? This is a non-crossing pairing. It doesn't have any crossings, right? So this is a subset of all possible pairings. And if you were to sum over all non-crossing pairings, then you would get exactly the analogous object of, as this, but for these semicircular systems. Right? And so this is a basic idea of free probability, I believe, due to Ronald Speicher. And basically, you know, what is, for example, if one thinks about these models of block matrices, right? So now I can also say a little bit about the proof. If you think about these models of block matrices I discussed before, if you were to take a Wigner matrix, D by D matrix, would replace every entry by a Wigner block and let the dimension go to infinity, what would happen is that when you compute the moments of these matrices, all of the pairings with crossings would become suppressed due to the non-commutativity of the blocks, and you would only have the non-crossing objects left in the limit. And that explains why these objects asymptotically behave like X3. But basically, what we are using implicitly, though we do not exactly prove it that way, is that if this parameter, the norm of the covariance matrix of X defined by the expectation of X squared is small, then the pairings are already suppressed, but the contribution of the pairings actually turns out to be controlled by this quantity over here, the norm of the covariance matrix of X divided by the expectation of X squared. And therefore, if this parameter is small, then the pairings are already negligible. And one does not have to take some asymptotic limit or something to see the behavior of free probability show up. And the main miracle here that you only need it to be as small as 1 over log D, not as 1 over D. That's the miracle here, that it actually takes very, very little for these pairings to disappear from the picture. And that's the magic of the story.
So, Ramon, now
Yes.
all your
may I ask, could you give a reference to the construction of X3?
Yes, of course. Look at the beautiful book of Nika and Speicher. It's called the combinatorial. Let me think about it. Nika. Lectures on the combinatorics of free probability.
So Roland Speicher is here. Maybe you have a comment.
Yeah, thanks. Thank you.
Yeah, maybe I can second this, that you should have a look on this beautiful book. Maybe there's been another beautiful book, which is by me and Jamie Mingo, which maybe is more general. And I think this operator valued stuff and these equations is actually more in a book with Jamie.
So I also recommend, but it had a big influence on us, is the paper by Hagerup and Thorbjornsen, which really emphasized the importance of this model X3, right? So for the introduction to all of these objects like free semicircular system, I definitely recommend this. And there is the famous paper of Hagerup and Thorbjornsen. I don't remember the title of it, but it has some title that you wouldn't recognize. It's called A New Application of Random Matrices. X of something is not a group, or something like this. I don't remember exactly what it is. It's in the Annals of Math, 2005, I think. This paper, X-free, played a hugely important role in that paper. And this paper contains the Dyson equation, and there's a paper of Lehner, which I cited earlier, which is also here, this theorem of Lehner here at the bottom over here. It's called something like computing the norms of free operators or something like this.
Ramon, I'd like to ask a question. Most of your formulas that you wrote down explicitly have a Gaussian flavor to them. How do you deal with the non-Gaussian case? Are there formulas like that for non-Gaussian problems?
So you know, the basic, okay. So here, at least in the results that we have already available in the archive, there's new results coming, hopefully. But so the question is, what model do you look at if it's non-Gaussian? If I gave you any model with no assumptions whatsoever on any distribution, I mean, you can cook up any kind of, weird counterexample, right? But it turns out in the applied math literature, there is a basic model that has turned out to be very, very influential, which is that if I take the random matrix X to just be a sum, I is 1 to n, of Zi, where Zi are independent random matrices. And I don't assume anything else. So just take a sum of independent random matrices. Of course, if n equals 1, this I've just described any random matrix. But when n equals 1, these results are not going to be good, right? But so just so you have it in mind, any jointly Gaussian, so the model I've been talking about, because I can always write a jointly Gaussian vector as a linear combination of independent Gaussians, I can always express such a matrix as a linear combination of deterministic matrices with scalar Gaussian coefficients. Right? So I can always think about a jointly Gaussian matrix as being a sum of independent Gaussian matrices where the randomness is even, right, just scalar, right? Or for example, a matrix with independent entries, but with any distribution, right? Right? I could write it as X is sum over Ij is 1 to D of the some scalar random variables times the rank 1 matrix, which just puts an 1 in the Ij coordinate, etc. Again, it's a sum of independent random matrices, but you can look at sample covariance matrices, right? So if x1 to xd are independent random vectors, and I take x to be the sum I is 1 or n, I is 1 to n of xi transpose. This is called a sample covariance matrix. Maybe subtract the mean. These are very important, for example, in mathematical statistics. And go on. So each of these is a sum of independent random matrices. Right? And if you think about it, right, I mean, if I were to divide, if they were, for example, IID, I were to divide by square root n and let n go to infinity, they would become Gaussian. The central limit theorem would kick in. Right? So the way that we deal with such models is we basically have a counterpart to this principle, right? So in this principle over here shows that under this very mild condition, or mild, okay, whether it's mild depends on the application, but in many cases it's very mild. Under this mild condition, the Gaussian random matrix X behaves like X free, right? So we have a complement to this, which basically says that there is some quantity, which is basically the maximum of the size of the Zi's divided by the expectation of X squared. If this is much, much smaller than 1 over log D to something, then the random matrix X that I wrote over here, which is non-Gaussian, behaves as a Gaussian random matrix with the same mean and covariance. And again, the magic here is that this condition only has a log D on this side, right? So this is like if I take a sum of independent random matrices, here I take the maximal size of the summons, and here this is like the sum, right? It's the sum of the squares, right? So as long as each of these summons is of logarithmically smaller size than the full sum, then already under such a mild assumption, the non-Gaussian matrix X behaves like a Gaussian random matrix with the same mean and covariance. And then we can apply the theory I showed you before to the Gaussian random matrix. The magic of all of these theorems is not so much that they exist, right? Because it's known, for example, that the central limit theorem kicks in if the size of these guys is of order 1 over square root n, right? Or 1 over square root d. And it's known that that you get free behavior if you have Wigner matrices, right? When the entries are of order 1 over square root d, right? But the magic of these kind of results that it's only 1 over log d is already enough to have these limit theorems kick in, right? So it takes very, very little for random matrices to behave like the ideal counterparts. And it's much better than you would get if you were to try to prove analogous results, for example, for random vectors rather than for random matrices. And so for some reason, random matrices have universal behavior in a very, very weak situation. That is much, much weaker than in the classical models that you see in random matrices. Does that make sense? So these are really two independent phenomena, but they're both rather weak. You know, under some mild assumption, models like this behave like Gaussian random matrices, and under such mild assumption, Gaussian random matrices behave like X-free, right? And you put those two things together, and you have rather general theorems. But this phenomenon here also reproduces things. If you've ever heard of the matrix-Bernstein inequality, this is one of those bread and butter results used in applied mathematics. It reproduces also this theorem. It's completely reproduced by this phenomenon over here, which means that it's really capturing the same type of models.
Thank
so
you.
we have ongoing work where we can deal with models that do not look of this form, that are non-Gaussian but do not look of this form, but are in fact okay. It's a long story, but it seems that's you know, there are two separate questions. Does the matrix behave like a Gaussian, and does the Gaussian behave like the free object?
So let's ask if there are other questions from the audience.
Perhaps a very general one, just to go back to your picture of Van Gogh.
Yes.
How much can you say about, or how close are these things to such a pixelated picture? Do they really behave in this way, or has it been tested? Just curious.
First of all, I mean, it was sort of a joke, the picture of Van Gogh. You would have to, first of all, divide it into pixels. And then you'd have to tell me, what are you making the intensity of the pixels? Is it the mean? Is it the variance? Right? I mean, I can play here with the mean and the variance. I can also play with the covariance. That's the dependence, right? So you know,
the obvious one would be the intensity, but
so the intensity meaning the variance. So let's say we could do independent entries with the variances coming from a Van Gogh painting. It should work very well, you see, because in order for this, in such a situation, in order for this to kick in, so let's just, you know, maybe this will answer the question. Suppose, now this is the one model that we had earlier results on, I didn't mention them. Suppose that Xij, remember X is, let's make it self-adjoint, okay, just for simplicity. It doesn't matter, let's not make it self-adjoint. So then we're looking at the singular values. If I'm not making it self-adjoint, I'm talking about the singular values. So let Xij be independent Gaussians with mean 0, but arbitrary variances, right? And I'm going to take these variances and make them the intensities of the Van Gogh picture. Does that make sense? So in this case, the norm of the covariance matrix of X is the maximum of Bij squared, because the entries are independent. So the covariance matrix of the entries is diagonal, right? It just has the variances of the entries on the diagonal, right? So it's the maximum. And in this case, the expectation of X squared, because it's not, I didn't make it symmetric, I really have, instead of the expectation of X squared, I would have to take the expectation of X transpose plus the expectation of X transpose X. This is the correct generalization of, in the non-symmetric case, right? So this is max of the sum of the variances along the rows plus the maximum of the sum of the variances along the columns. So our theory kicks in as soon as the largest variance is at most 1 over some power of log d times the largest sum of the variances in a row or column. Does that make sense? Now, in a Van Gogh painting, right, you would have to be extremely sparse for it, or you know, for this not to be true, right? In a Van Gogh painting, that will almost assuredly be true. So, I mean, I didn't actually try it on a Van Gogh painting. Maybe I will one day, just as a joke. But But you see, I mean, basically, if for example, just for simplicity of notation, we do assume that the matrix is symmetric, right? For the theory to kick in, you would need that the maximal variance is smaller than, let's say, 1 over log d cubed times the maximum sum of the variances. So in order for this not to be true, right, every row would just have to have one very large entry, and the remaining entries would have to be very small, right? Or just a very small number of large entries, and the remaining entries would have to be very small, right? That doesn't seem likely for a Van Gogh painting.
Perhaps I can ask a very
some idea
different
about how weak these inequalities are. That's, for example, if I take a band matrix, right? It's just a random band matrix, right? So I have a d by d in the band matrix K, right? So of course, if K equals 1, I have a diagonal matrix. And we know for diagonal matrices, you know, they don't behave anything like X3, right? So if K is small, then of course it should still not be true. But as soon as K is let's say logarithmic in D, our theory starts kicking in. So you need logarithmic in D, and that's necessary. I mean, if K is much smaller than log D, then it's known that it cannot behave at all like a random matrix. And as soon as K is larger than log D, so our theory here gives log D cubed. For the independent case, we have completely different method of proof that gives the sharp log D behavior, right? But it requires much stronger assumptions, right? But this showing that as soon as K, let's say, is much larger than log D cubed, our theory kicks in, and this log D is much smaller compared to the dimension. So that gives you some order, some idea of the limitations and the scale at which these type of phenomena. I think if you want to make an analogy with mathematical physics, you know, our theorems tell us when random matrices behave in a mean field way, in a kind of, these are kind of mean field theorems for random matrices. You know, in mathematical physics, which is a completely separate story, but you know, you have some models of statistical mechanics have mean field behavior. If you assume mean field behavior, often you compute analytically everything there is to compute, right? And then you want to show when do models behave like mean field. And what our results show is that for random matrices, that happens under very mild conditions, right? So that's the X3 is like the mean field object associated to the random matrix.
So essentially, it's that you're testing that your covariances of your planar diagrams are playing the role in your covariance in some sense. That's what you told us.
Basically.
But can I ask you, has this been applied to multi-matrix models?
No. I'm not sure what a multi-matrix model is.
Well, you can probably map it into a lot of them into ones where you make a matrix out of blocks in a particular structured way. You have many matrices, and you can regroup them into some sort of larger matrix with maybe lots of zeros.
So then it should apply, right? Because then, right, in general, but this is getting us closer to things that were already known in free probability, I think. Yes. Right. What is a multi-matrix model? What do you call a multi-matrix model?
Well, you take a family of matrices, such as for one matrix, you have Hamilton, you have Cayley-Hamilton theorem, where the traces related to something like that. Whereas multi-matrix, you can take products of matrices, lots of traces, and the traces.
So let me make a statement here, right? So here is the kind of, I mentioned this, but very briefly, maybe it wasn't clear. Suppose I take a bunch of xk, let be independent random matrices, and each of them, so they're independent. These are d by d random matrices, independent of each other, right? But each one of them each one is jointly Gaussian, has jointly Gaussian entries. They can have different means and covariance matrices. So I'm not assuming they have the same mean and covariance matrix. Just each one has jointly Gaussian, they're independent of each other. Each one has jointly Gaussian entries, and each one of them satisfies this condition that we need in order for it to behave well. Right? Then our theory actually says that if P is a non-commutative polynomial, let's say a self-adjoint non-commutative polynomial, just so it has real eigenvalues, then for any such polynomial, if I take that non-commutative polynomial of these independent random matrices, then the spectral distribution or whatever other things you want converges to the same object. Well, converges, is close to, right? Under this condition, is close to in a quantitative, there's no convergence here. Is close to in a quantitative sense, the same object with the free.
Yes.
Now, unlike in the case for a single matrix where you have matrix Dyson equations, computing the spectral distribution of these polynomials can be a real pain in the ass. But this is something that you can extract from the type of theory that we're doing. Right?
Well, this is all very interesting. I think we're going to have to cut off the discussion at this point, but we'll look forward to all the new results coming out of this theory. And thank you, Ramon, for telling us all about this.
Thank you very much for the invitation and for all the questions.
Yeah. Bye-bye. Bye-bye.
Bye.